Hi everyone, so today I have quite a fun question for you, and we're going to deal with primes and modular arithmetic. Now whenever you hear these two quantities, probably the first thing that strikes your mind is Fermat's theorem, right? Because you have prime, you have this congruence modulo. FLT is probably something that comes straight up to your mind. And yes, you would be correct. This is going to be a little bit about Fermat's theorem as well. So without wasting any time, let's just get right into it. This is a question from the Singapore TST, day 1 problem 3 in the year 2008. And in this video, we're going to be talking about what primes and perfect squares are, a little bit about Fermat's theorem and modular arithmetic, divisibility and reducing mod P, parity, and Euclidean division algorithm. And then we obviously have book sessions for senior math Olympiads, and at the end, a similar but challenging problem. So quite a little bit to discuss over here.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, cool. So we need to find all primes P such that P divides this entire summation. And so P is dividing a summation, it's dividing the entire sum and not an individual element of it, right? Now, a couple of things that you should, keep in mind, a couple of things that I would observe when I see this problem. I have a P minus 1 in the exponent. Whenever you see a P minus 1 in the exponent, Fermat's little theorem is probably something that should click naturally to you, right? Because what is essentially Fermat's little theorem? It is basically A raised power P minus 1 is congruent to 1 modulo P, and that's it, as simple as that, right? So whenever we have this P minus 1 exponent, it kind of brings us back to this elementary result in number 3, which is Fermat's little theorem. But okay, other than that, let's try to make some tangible progress over here. So they've given us that P divides the sum. Now, in language of modular arithmetic, what would that mean? That would mean the summation from n is equal to 1 to 103 of n raised power P minus 1 is congruent to 0 mod P, right? Because the remainder is 0, P divides this entire summation. Now I'm going to do something pretty interesting. I'm really going to divide this sum into two components, right? I'm going to state it as summation from n is equal to 1 to 103 of n raised power P minus 1 such that this prime P does not divide n, plus the summation from n is equal to 1 to 103 of n raised power P minus 1 so that this prime P actually divides n. I was just writing this entire sum like this because P can either divide n or it won't divide n, right? It's as clear as that. It can either divide n or it won't divide n, and I've just split it up into two, you can call it two subsets, really, two classes. And when you take the union of them, you get the original summation, right? Because there are really no other possibilities. Okay, but now what we can do is we can analyze this a little bit one by one, right? So just consider this summation where P divides n. If I just consider this, if I just maybe try to highlight what is going on over here, this means that P divides n, right? So in a way, n is a multiple of P. That's just another way to state that. So we'll have P, 2P, 3P, 4P, and so on and so forth until you get to floor of 103 divided by P times P. And what does this mean? What's the interpretation of this? This is the largest multiple of P that is less than 103, because we are essentially summing up to 103, right? Because it obviously can't be greater than that, because we have P dividing an n and n is going up till 103, so it obviously can't be greater than 103, right? A factor of it. So n is effectively a multiple of P, and at max it can be floor of 103 by P times P, which essentially is just the mathematical way of saying that that this is the largest multiple of P that is less than 103. Okay, amazing. Now, so how many elements are in this set? So you have P, 2P, 3P, or in other words, if I just ignore that P, I have 1, 2, 3, 4, 5, 6, all the way up till floor of 103 by P. Therefore, we have floor of 103 by P elements in this set, right? In this set, which I've denoted by n over here, this has floor of 103 by P elements, right? Now this original sum has obviously 103 elements because n is going from 1, 2, 3, 4. After a point, you'll get 100, 101, 102, and 103, right? So at the end of the day, this has how many? 103 elements. If this has 103 elements and this thing over here has floor of 103 by P elements, what does this mean? That this has 103 minus floor of 103 by p elements. So because total, when you take the union, you need to get 103 elements. So you have 103 by p, the floor of 103 by p for this summation, and for the other summation, you would obviously have 103 minus that quantity, right? Because when you take the union, you need to get the original sum, right? So we have 103 minus floor of 103 by p elements over here. Now, once all this discussion is done, let's come on to the main thing. So I'll just rewrite the sum once more. N is equal to 1 to 103 of n raised to p minus 1 such that p does not divide n, plus floor n is equal to 1 to 103 of n raised to p minus 1 such that p actually divides n. Now what we're going to do is we're going to reduce modulo p. Now if p divides n, would this be 0 modulo p? Because for example, n is some multiple of p. Let's say n is equal to kp, right? So it will be like summation from, let's say, n is equal to 1 to 103. If I just replace this as kp raised to p minus 1, right? So it is obviously going to be, the remainder will be 0, right? If you take the mod p over here, you get 0. The remainder will be 0 because you have effectively a power of p, right? Any power of p, you divide by p, the remainder is obviously going to be 0, right? Effectively. So my entire point is that when p divides n, this entire thing is going to be 0 mod p, right? It's as clear as that. This entire thing is going to be 0 mod p because effectively p is dividing n, or n is a multiple of p, and when any multiple of p is divided by p, the remainder is always 0. So you get clearly 0 modulo p. Now from Fermat's little theorem, I know that n raised to p minus 1 is congruent to 1 mod p, but I also know that this p must not divide this n, and that is essentially the key idea why I split this up into two cases, because we can't directly apply Fermat's little theorem. Mind you, Fermat's little theorem is not applicable when p divides n because it's 0 mod p, like we just saw that very clearly, right? It's pretty obvious. But Fermat's little theorem can really only be applied when this p is not dividing n, or in other words, the GCD is actually equal to 1. It's equal to unity, right? So you can just apply Fermat's little theorem over here, and how will that look? Well, the summation from n is equal to 1 to 103 of n raised to p minus 1 such that p does not divide n, that would be congruent to L1 plus 1, plus 1 all the way, plus 1 plus 1 dot 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 modulo p, because effectively you're just using Fermat's little theorem, right? And Fermat's little theorem tells us that remainder is 1. So, and these, because it's a summation, it gets just added. And how many elements are over here? You have 103 minus floor of 103 by p elements over here. So basically 1 plus 1 plus 1 plus 1, how many times? 103 minus floor of 103 by p times, right? Because this set, this p does not divide n. Let me just remind you, this p does not divide n. This quantity, that set, it has 103 minus floor of 103 by p elements, and that's why this discussion of elements over here was quite important, right? Otherwise you probably wouldn't have seen that. But now, because we have 103 minus floor of 103 by p elements over here, I can effectively just state that the summation from n is equal to 1 to 103 of n raised to p minus 1 is effectively congruent to 103 minus floor of 103 by p modulo p. But we want this to be 0 mod p, right? We want this to be 0 mod p because p needs to divide that summation. P needs to divide that summation, so well, we can just directly state that 103 minus floor of 103 by p needs to be congruent to 0 modulo p, and that essentially implies that 103 needs to be congruent to the floor of 103 by p modulo p. So do you actually realize what we've done over here? We've effectively simplified this complicated looking summation and this prime and all of these things into a simple congruence equation. Now all we need to do is find all primes p that satisfy this equation, and we are done. We are done. That's all we really need to do, right? We need to just find all primes p that satisfy this given equation. Obviously it's easier said than done, but we've at least made some progress into this, right? Okay, now we're just going to use a little bit of concept of this Euclidean division lemma and all. So I can write 103 as ep plus r, where p is our prime that we need to find, and r is obviously the remainder. So this is between 0 and p minus 1, something that you will be aware of. Okay, amazing. Now what I'm going to do is I'm just going to take mod p on both sides. So 103 will obviously be congruent to r modulo p, because this thing will obviously be 0 mod p. It's clearly divisible by p. So 103 will be r mod p, and keep that in mind, right? Now Now what I'm going to do is, because I have this thing 103 is equal to AP plus R, I can really divide by P on both sides. So I'll get 103 by P is equal to A plus R over P. And let me just take the floor on both sides. And really why I'm doing this, because we have this floor 103 by P, right? On one of the sides over here. We have the floor 103 by P. So just try to generate, some terms similar to that. Now A is an integer. So floor 103 by P can just be written as A plus the floor of R over P. It just comes out. We know that from the properties of the greatest integer function. That being said, R is less than or equal to P minus 1, right? From this, the condition of the Euclidean division lemma, we know that R is less than or equal to P minus 1. What does that mean? That means the floor of this is 0. Because that quantity will be obviously less than 1. But effectively means that the floor of 103 by P is effectively equal to A. Okay, now if I remind you of the congruence equation, we had 103 is congruent to floor of 103 by P modulo P. Also, we had received this result that 103 is congruent to R modulo P. And we also know that floor of 103 by P is equal to A, right? Floor of 103 by P is equal to A, and the other result was 103 is congruent to R modulo P. So if I just incorporate this over here into our goal equation, 103 is congruent to this thing modulo P, and 103 is congruent to R mod P. So and this thing is equal to A, or an equivalent way of stating that is R is congruent to A modulo P. They essentially leave the same remainder, right, when divided by this quantity P. Or in other words, A is congruent to R modulo P. Right, I can just state that as well. That implies that A is equal to some quantity B times P plus R. Because you have A is equal to BP plus R, you take modulo P, you get A is R mod P, and that's just an equivalent way of writing that. Now it becomes fairly easy, and I'm just going to label certain equations over here. Where do we go? Let's say, let's call this equation as number 1. 103 is equal to AP plus R, the thing that we have essentially started with. And let me just write that down as well. AP plus R, this was my equation number 1, and A was obviously BP plus R. Now really we're just going to split this up into two cases. Case 1 B is 0 and case 2 B is non-zero. Right, as simple as that. So if B is 0 and A is equal to BP plus R, that essentially implies that A is equal to R, right? Because B is obviously 0. So that means 103 is equal to AP plus R is equal to A. So 103 can be written as A times P plus 1. Now P is a prime, and it is to be noted that 103 is also a prime. So 103 can only be factorized as 103 times 1 is equal to A times P plus 1. So it's clear to see that A needs to be equal to 1 and P plus 1 needs to be 103. So P needs to be 102, but P is a prime, 102 is not a prime, and hence this case fails. Therefore, we have 0 solutions from case number 1. B is 0 does not work. It clearly does not work. We were trying to find some trivial solutions, but it clearly does not work. You can now generalize this. You can take case 2. B is greater than or equal to 1, because obviously B has to be a natural number. And to remind you, A is equal to BP plus R, right? A is equal to BP plus R. Let me just maybe put that as equation number 2. Why not? Right? Now what I'm going to do is I'm going to put this value of A is equal to BP plus R into this equation. I'm just going to substitute that over here. So we had A is equal to BP plus R, and you had 103 is equal to AP plus R. Right, let's just put in the value of A. So you'll get 103 is equal to BP plus R times P plus R. So you get this kind of quadratic looking expression. 103 is equal to BP square plus RP plus R. But that effectively means that 103 is greater than P squared. It's clearly greater than P squared, right? So because it's a multiple of P squared plus another term of P, and then you have this constant term as well. So it's clearly greater than P square. Or in other words, P square is less than 103. And mind you, P is a prime. Therefore, P can only be from the set 2, 3, 5, 7. Because the next prime 11 squared is obviously 121, which is greater than 103. So P can only be 2, 3, 5, and 7. And now it is just elementary casework. Now I just need to plug this in and figure it out. Right, we just need to plug in the value. So for example, value number 1, P is equal to 2. 103 mod 2 is clearly 1. Right, floor of 103 divided by 2 is what is this, actually 51, and again 51 modulo 2 is again 1. So P is equal to 2 clearly works, and actually P is equal to 3 also works. I'll leave that up to you to check that out. P is equal to 5 actually does not work, and our fourth value was p is equal to 7. This also does not work, and I'll actually just demonstrate that to you. So 103 mod 7 so happens to be 5, because 14 7s are 98, because it's divided by 7 you get remainder 5, and 103 by 7, when you take the floor you get 14, and 14 mod 7 is obviously 0. So we have 5 and 0, so obviously this also clearly does not work. So the only thing that does work is p is equal to 3 and p is equal to 2. So therefore p is equal to 2 and 3 are our two and only solutions, right? Are our only solutions. So after all of that, putting the pieces together, what we realize is the two smallest primes, p is equal to 2 and 3, are the only primes that satisfy our given condition that p needs to divide that sum, right? So quite an interesting equation. And the key idea was to use this Fermat theorem and to kind of get to that simple congruence equation, because once you get to a congruence equation you can solve this in a few ways, but the major idea I believe was figuring out Fermat theorem and really reducing this down to something simpler, something that we can deal with. So I really hope you like that. Okay, so moving on to some book suggestions for senior math Olympiads, we have I'm a Compendium, Polynomials by Barbeo, Elementary Number Theory by Sierpinski, Graph Theory by Harari, Combinatorics by Brualdi, Secrets and Inequalities, and Functional Equations and How to Solve Them by Christopher G. Small. Okay, so at the end we have a similar charging problem, and I want you to find all primes p and q such that this quantity 3 raised power p, 3p times raised power q minus 1 plus 1 divides 11 raised power p plus 17 raised power p. So again, maybe try using Fermat's theorem a little bit over here, and if you're able to do it, let me know, because 11 is a prime, 17 is a prime, you have this quantity p is also a prime, q minus 1 again a prime minus 1 in the exponent. It's literally screaming to you that you need to apply Fermat's theorem. So there's very direct intuition for this. So maybe try this out, and if you're able to do it, let me know. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.